So we talk about the magnetism of the Earth, 地球的磁场。So actually, it mentioned that we have two types of pole for the Earth. Yeah, we have a geometric North Pole, South Pole, or the magnetic South Pole, North Pole. Actually, they are not the same point. Actually, they are not the same point. So in this case, if you use a magnetic stick and then go to maybe somewhere here, then you get the wrong direction. Actually, 就是那个地理的北极、南极跟那个磁场的南极、北极，它们是不一样的，and actually so there is a few declination， 有一个倾斜的角，and actually the magnetic field, the direction of the magnetic field generated by the Earth is changing over time. Of course, for a human being, we cannot sense it, but for quite a long time, actually the magnetic field of the Earth is actually changing. Yeah, so it is related to a interesting phenomenon, which is called aurora, 极光的现象。Actually, it's something like the high energy charged particle moving close to the Earth. So you can imagine, suppose there is a charged particle going this way, approaching the Earth. Maybe something like I'm not sure, something like high energy charged particle, maybe gamma ray or I'm not sure whether it's charged or not. But for high energy charged particle, as long as it's approaching the Earth, if it is inject to human body, then it may cause some sort of cancer, skin cancer or whatever. It's not good. And actually, the magnetic field of the Earth acts as a shield for the Earth. 就是像个盾牌那样，把一些高能的带电荷的粒子，把它也不是反射，它是 redirect， 就是让它走另外一个方向。So you can imagine using the Lorentz force. So as long as the V is in this direction, maybe it's positive or negative. Assume it is positive, then the B field at this point should be like this. So maybe upward. So you can have V cross B, so that there will be a force acting on this charge going this way. So it will try to redirect the charged particle to go away. If it's negative, it will go to another side. So it will try to. So if this charged particle is directly from the side of the magnetic dipole, so it can be direct. But if it's going from this way, then this side it cannot be direct, because you can imagine V cross B is somehow in the same direction or opposite direction. Then the force will be very small, so that it will not redirect much, and then it will hit the Earth. So that is just like the weak point of the Earth. 就是有一个弱点，就是头顶跟脚底，它就是有一个罩门在，从那边打过来的话，它就没有办法把它挡出去，那 so actually the geomagnetic North Pole is somewhere near have an angle of 11.5 degrees with the geometric North Pole. So the South Pole of the Earth is northern hemisphere. South Pole. Yeah, actually the South Pole of the dipole is in the northern hemisphere， 在北半球的那个南极。所以磁力线是从 地理的南极跑到接近北极的地方啊。So actually near the 就是那个北极圈附近的地方可以看到极光现象，就是那些高能粒子在电离那个大气层，所以看太多的话对身体不好啊，偶尔看看也 OK。你去动物森友会看也可以啊。So actually this is even more hardcore. Actually this stuff comes from the quantum mechanics. So I cannot explain you why it's like this, but the physician try to explain how does the magnetic field comes from? How does the magnetic field come from? So for electric field, it is easier to explain because we can find charge. We can find the electron. So it has elementary charge. But for B field, how does it come from? This is a problem. So in that case, they try to explain it using the spin. Actually, you not only need to use the Schrodinger equation to quantum mechanics, you also need to add some relativistic effect so that there will be some sort of spin magnetic dipole. 所以就是除了量子力学之外，还要用那个相对论才能够解释那个自旋想推导出来的。就是你高中的时候可能学过一些什么量子数啊，什么角动量子数啊，什么 MLMS 那些，就是解那个 Schrodinger equation， 然后 given 一个氢原子的那个位能，然后解出来的，然后解的过程非常复杂，要用一些什么级数去解。And actually, the spin is even more complicated too. So I don't really know how does it come. So it's just like this is the spin, and this is the elementary charge, and this is the mass of the electron. This is the mass of the electron. So it is somehow like a unit magnetic dipole, which comes from the spin of an electron,所以就是电子自旋的时候，它就会产生一个磁场，然后可能有很多不同的电子，它都在同一个轴上面都往同一个轴上面旋转，那个磁场就会叠加。如果它是很乱的，它就互相抵消，那外面就看不到有磁场的出现。So it's somehow like that. Well, yes. So it's very complicated. It mentioned that we cannot observe actually what S is. We can only observe S in maybe Z direction or in a single direction. So actually, in a single direction, we always observe this spin is quantized. 就是角动量子化怎么出现我也听不懂，非常复杂。So ms is either plus or negative 1/2, plus or negative 1/2, and h is the Planck constant 6.63 times 10 to minus 34, and this is 2 pi. So in chapter 38, I will also talk about the quantum mechanics. So I'll use another notation called h bar to specify h over 2 pi. Yeah, so this one is called a reduced Planck constant. So we only divide h by 2 pi. But what this is, I don't really know. So actually, so we have the Bohr magneton, and this comes from another stuff is somehow like So actually it's somehow like the unit magnetic uh, dipole. So this is called the mu b, as long as we have this sz and then we substitute this stuff into here. So we can got mu b to be this one, and the value is somehow like 9.27 times 10 to minus 24, somehow like a elementary charge in magnetic field. Yeah. So of course, as long as there is a magnetic dipole, then you can find the energy. And the other mechanism for generating B field is that an electron is moving circularly to something. It's just like an atom. We have electron rotating around it. So this movement will also generate the magnetic field. And the term is somehow similar, E over 2m times L. At this part, E over m times S. Here we have S somehow like this. And here we have L to be ml times h over 2 pi. So it's somehow like ml h bar, ml h bar. And ml should be 0 plus or minus 1 plus or minus 2. So this stuff you may have learned it in high school in the chemistry class, but actually you don't know what it is. You only need to know how to allocate the electron on this somehow 1s, 2s, 2p, somehow like that. Yeah. But actually, for the physician, they try to analyze it in a physics way. What is the electric field, magnetic field, somehow like that. So as long as we also have the magnetic dipole due to the orbital movement, so we can also calculate the energy. So next is three type of magnetism. So this one is called diamagnetism. 这个叫抗磁性。So in this figure, you can see a flock, a special type of flock. I don't know what it's called. I did not mention here. So it's a special type of flock. And then this flock has some material which is diamagnetism. And then this one generate a uniform E field, and the flock is floating. 我记得这一个是有拿那个搞笑诺贝尔奖的，然后那个人后来有拿真正的诺贝尔奖，拿搞笑诺贝尔奖就是按照这个来的，那 the diamagnetic material plays an external magnetic field, B external, develop a magnetic dipole moment direct opposite to the B external. 非常复杂，那我用中文讲，不然我用英文讲完大家都听不懂嘛。他是说那个抗磁性的物质是，那个物质在那边，那我物质在那边，那我产生一个磁场在那边，就可能通过它，那它抗磁性，它就会自动产生一个反向的磁场，跟你外来的那个方向相反。 所以当你当这个青蛙，这个是青蛙，就是虽然不像，你产生一个磁场在那边的时候，它就会产生一个反向的磁场。那反向的磁场，它们就会互相类似排斥的感觉，那它就让它浮在空中，浮在空中。Also, it's called the levitating flock. Where the flock was placed in the diverging magnetic field near the top of the vertical current carrying solenoid. So this is 这个是一个线圈，它产生一个类似固定的磁场啊，所以 so every atom in the flock was repelling upward away from the region of the stronger magnetic field at the end of the solenoid. 所以就是把那个青蛙浮起来，然后他说the frog is not in discomfort because every atom is subject to the same force, and thus there is no force variation within the frog. Okay, so so there are still two types. So the second type is called the paramagnetism. Paramagnetism 就是这个叫做顺磁性。那顺磁性跟刚才的抗磁性相反。抗磁性是你 external B field 产生了之后，它产生个相反的方向的磁场。那顺磁性的话，就是说你产生你给它一个 external B field， 它就会有一个跟它同一个方向的磁场会产生，那这个叫做顺磁性。So a paramagnetic material placed in an external magnetic field B external develop a magnetic dipole moment in the direction of the B external. If the field is non-uniform, the paramagnetic material is attracted toward the region of the greater magnetic field from the region of the less field. 所以它的现象就会变成说，它们会互相吸引的，刚才那个是互相排斥的，那这个会互相吸引。So paramagnetic material. So align. So originally all the permanent magnetic dipole moment are randomly oriented. So if you do not apply an external B field to it, all the dipole moments are aligned randomly, so that most of them will be cancelled. If not all. But as long as you apply an external B field, they will start to align, and then they will have generate some B field due to the material itself. And so actually the Curie, Mrs. Curie 就是居里夫人啊 ，Mary Curie，然后就是她就是发现那个镭可以做那个 X 光那个人嘛，然后他是一个拿过诺贝尔物理奖跟化学奖的人哦，很少数拿个2个不同的诺贝尔奖的人。那这个是说，这个线叫做 Curie's Law， 当时还没有量子力学。那他当时可能观测到这里，他就觉得他们是线性的关系。They feel like a linear relationship, so that she used a external expression to express the generated B field over the external B field, somehow like that. And then it should somehow be a linear relationship. But later on, as long as we can maybe generate an even larger B field, we find that this will not increase without limit. Actually, it will start to decay. And actually, we really need the quantum theory to explain this phenomenon rather than using this equation. So all the stuff are very physics, very hardcore. Actually, I have not learned it before. Hmm? Okay, so there is a simple sample problem, but yeah, so I just finish it. So a paramagnetic gas at the room temperature 300 Kelvin, is placed in an external uniform magnetic field of magnitude B equals to 1.5 T. The atom of the gas have a magnetic dipole moment like this. So calculate the mean translational kinetic energy of an atom of a gas. The energy difference delta UB between parallel alignment and anti-parallel alignment of the atom magnetic dipole moment with the external B field. Also calculate the mean translational K. So according to the thermodynamics, 热力学，我们会知道那个 kinetic energy 动能是3/2 kT， 那 K 是那个波兹曼常数 Boltzmann constant 然后 T 是那个绝对温度，所以它是3/2乘以什么1.38 okay, somehow like this times 300. So actually the answer will be 6.2 times 10 to minus 28 joule. And next, delta UB will be minus mu B. So mu B cosine 180 degree minus mu B cosine 0 degree. So this is how we consider the potential energy. Suppose we have a magnetic dipole in the B field, so we can calculate the final potential energy, subtract the original potential energy, the initial potential energy. So this is -1, this is 1, so it becomes 2 mu B. So 2 mu B, which is actually 2 times this mu B is 9.27 times 10 to minus 24, which is the megatron. You can regard it as a unit of the magnetic dipole. And times 1.5, which is the B field. So the answer will be 2.8 times 10 to minus 23 joule. So the last type of the magnetism is called the ferromagnetism. Actually, we use it quite often. Actually, maybe 10 or 20 years ago. Yeah, actually, now I think we are still using it, unless your computer use the SSD drive. Actually, the hard drive use the ferromagnetism. in Chinese is called 铁磁性. So as you can see, ferro it means 铁嘛，铁. That's why the iron 的那个叫什么？科学名称还是 Fe 嘛，就是用 Fe 嘛，所以 ferro 就是铁，那个叫做元素的名字吗？还是叫什么？我已经忘记了那个中文名字是什么？它的名字是什么？So a ferromagnetic material placed in an external magnetic field, B external develop a strong magnetic dipole moment in the direction of B external. If the magnetic field is non-uniform, the ferromagnetism will attract toward. So it is somehow similar, but not actually the same. In this point of view, this is similar to the paramagnetism of a greater magnetic field from the region and less field. So as you can see, actually this graph is what I want to mention. This is called the hysteresis effect， 那个叫做磁际效应，气载效应。So actually, at the very beginning, it's if you don't apply the B field, if you don't apply the B field to it, you cannot it will not generate any B field. But as long as you generate an external B field to it, then it will then even after you remove the external B field, it will generate a B field at one of the direction. So it's called hysteresis, and then you try to apply the B field in opposite direction. So it will try to decrease as long as you generate the so actually if you apply the B field from 0 to maximum, it generates a B field like that, and you try to decrease to 0, it still generates some of the magnetic field. Try to generate some of the magnetic field. And the point here is that you generate a opposite direction B field for some amount. It can make the B field generated by the ferromagnetism material to be 0. And as long as you generate the negative direction B field to here, it will have also magnetic field like this, and then you remove it to generate the B field in this direction. So it does not only depend on how large the magnetic field you generate at that moment. It also depends on the state before that. So it's called the hysteresis. 所以就是那个硬碟或者是用磁力去记忆的那些装置的话，它的原理就是，我想要这一块它记住一个1或者一个0，那记住1的话，我就在那边就加一些磁场给它。那是写的过程，写完之后它还是会在这个地方。那你读这个磁场是正的方向，那它是1。然后如果我想要写个0那我就产生一个反向的磁场给它。那我写完之后它就会产生一个0在那边。所以hard disk 就是过去用或以前用的是磁盘，什么3又1/4寸，3又1/2寸，3.5，还有再旧一些的是5又1/4寸，有没有看过？我小时候的时候是5又1/4寸啊，那一张它可能只有几百 K 的因为3.5也没有很大，3.5只有1.44 M， 所以也很小。 那 hard disk 的话相对多一些啊、那用磁性的话就是用这个原理，所以你不能够拿个磁铁放在那个硬盘的附近，那就会弄掉它原来的资料，因为它就是依赖那个磁强去写资讯。你拿个你就是开地图炮，把所有的都变成同一个一或者零。So do not return complete. So it actually do not completely to return completely to the original configuration, even without applying the external B view. So you will stay at here and there, so that we can read the data we store in the ferromagnetic material. So, but retain some memory of the alignment after the initial increase. This memory magnetic material is essential for magnetic storage of information.